Hello, my name is Diego Ramirez. Today we're going to talk about the production of ATP, also known as adenosine triphosphate. So let's get started. So glycolysis is the breakdown of blood glucose, or actually glucose. In this case, we're going to use blood glucose to get some energy going. ATP must donate a phosphate to phosphorylate glucose into glucose 6-phosphate. If it was a glycogen, so glycogenolysis, the process would actually start here at glucose 6-phosphate. So we would need this ATP to be donated. But since we're starting with blood glucose, it gets to glucose 6-phosphate. Isomerase comes in, this enzyme comes in and turns glucose 6-phosphate to fructose 6-phosphate. And then again here, fructose 6-phosphate gains a phosphate under the control of phosphofructokinase, also known as PFK, and changes this fructose 6-phosphate into fructose 1,6-diphosphate. So the di means that there's another, now there's two phosphates that were just created. Aldolase is the one here that helps us with this split of these two fructose 1-diphosphates split into two 3-phosphoglyceraldehydes. Okay, so that's why we have two pathways here, okay, that represent each one of these 2,3-phosphoglyceraldehydes. Okay, NAD catalyzes and turns NADH plus, so gains some hydrogens to get sent to the electron transfer chain. Okay, also here phosphoglycerate kinase. Okay, there's some energy that is lost, this heat obviously. ADP picks up and creates one ATP and another one right down here, pyruvate kinase. So this phosphoglycerate is actually essentially decomposing, breaking down to usable pyruvate to go into the Krebs cycle, which we'll talk about. So in this rapid glycolysis here, we have 4 ATP that get generated because there's two 3-phosphoglyceraldehydes. However, we have 4 that got produced, but we got 2 that were donated, so we only have a net of 2 that were gained. All of this happens in the cytoplasm, so it's outside the mitochondria. Mitochondrial membrane, pyruvate goes through. There's an intermediate step that happens. Pyruvate dehydrogenase is here to, again, catalyze NAD plus to NADH plus. Again, to send this to electron transfer chain to generate energy. Okay, 2.5 ATP per NADH plus. Okay, and then once that happens, some CO2 forms. Coenzyme A binds to pyruvate to form acetyl-CoA. Okay, so acetyl-CoA here. Now, once that binds, the acetyl portion of acetyl-CoA binds to oxaloacetate in the Krebs cycle to create citrate. Here in the citric acid cycle, also known as the Krebs cycle, here there's all these reactions that are happening. What's the main goal? The main goal is to send these NADHs and this FAD2 out to the electron transfer chain to come back and produce, so they can go and get some ATP so we can utilize for energy. ADP binds to an inorganic phosphate through succinyl-CoA synthase to produce an ATP here in the middle of this cycle here. All this happens in the mitochondria. So all these cycles, pretty much beta oxidation and rapid glycolysis go through this. Okay. So rapid glycolysis is utilized mainly for short, sprinting at the end of a mile run, swimming all out on a 50 or 100-meter swim, sprinting up to 200 meters. That's where rapid glycolysis. Now, glycolysis, it's pretty much crucial during maximal effort for physical activity that happens for maximal physical activity, for about 90 seconds max. Then after that, lipolysis comes in. We got a triglyceride, so it has a glycerol, and three free fatty acids here. We're going to be dealing with a 16 carbon chain of palmitic acid, and glycerol gets stripped over here by glycerol kinase and gets shifted and shuttled to the glycolysis. And we'll talk about that in the next slide. To activate these free fatty acids, 2 ATP must be used. They come in and they activate the free fatty acids to send them through the mitochondrial membrane. We're not going to talk about this first few steps here because glycerol kinase comes in the form of 3-phosphoglyceraldehydes. So again, we have now moved our second because there's only one molecule here of glycerol. So same process, same thing happens. It goes through the same steps. Again, ATP, that's what we're looking for to generate. This happens in the cytoplasm, of course, and then the citric acid cycle or the Krebs cycle for that glycerol comes in and goes through the same cycle here. So all these ATP are getting produced in the mitochondria. Just a quick note here, dehydrogenase, that's where you can see that these NADs and H2s are actually being essentially catalyzed, and they're going to the electron transport chain. For the FADH2, 1.5 ATP get produced versus NADH+, where 2.5 ATP get produced. Beta oxidation, that activated fatty acid, coenzyme A comes in and shuttles this 16 carbon activated fatty acid in twos. So pretty much into pairs of 2 carbon acyl groups to the Krebs cycle, where it binds to acetyl-CoA. And coenzyme A here, again, this is where it goes, boom, binds, and gets sent to the Krebs cycle. 7 times it goes. This one, the acetyl-CoA goes through it 10 times. Okay, because it's or not 10 times. Sorry, it goes through 8 times. However, it gives 10 Krebs, 10 ATP. And then for here, it only goes around beta oxidation. Oxidation means oxygen. So to catabolize fat, oxygen must be utilized. So lipolysis gets utilized with 30 to 80% of the energy for biological work. And obviously depends on a person's nutritional status, their level of training, and intensity and duration of physical activity. So for example, somebody that is doing an Ironman triathlon here has to train their systems to utilize lipolysis more effectively to generate energy so they can complete their event. Fat becomes the primary source of fuel for exercise recovery when intense long-duration exercises depletes glycogen. So when glycogen is no longer there, then lipolysis is the main source of energy. Why can't we just utilize the same amount of energy, or let's say ATP here? ATP from one molecule of glucose yields 32 ATP. Actually yields 34, but because we use 2,2-phosphorylate glucose, 2 ATP, so 34 minus 2 is 32 ATP. And then glycerol yields 19 ATP from glycolysis and from a Krebs cycle. And then free fatty acids, because we're doing 8 pairs of palmitic acid, 16 carbon chain, 10 ATP from the Krebs cycle alone. And so Krebs cycle gives us 80 ATP, and beta oxidation, because again, it only goes through 7 times and then yields 4 ATP per cycle. It gives us 28 ATP. So for a total of 125 ATP. Why can't we utilize just fat for energy? Because again, if we're doing long duration exercise, of course, we're going to be able to maintain that because there's oxygen that it keeps coming into catabolizing fat. However, if we're doing it to, let's say, a sprint, and I can use an example as a sprinter. Yeah, why can't a sprinter depend on fat? Because it's too long. It's a slow process, and versus rapid glycolysis, it can actually give you energy right away. Again, as we saw, up to 90 seconds of energy glycolysis could be utilized versus the fat catabolism takes a bit longer, and so that's one of the main reasons why we cannot utilize fat as a main source of energy for like short bursts of energy lasting less than 90 seconds. This concludes the presentation. If you have any questions, please let me know. Here's my references, and thank you very much for watching my presentation.